I was planning to do like close up the complex analysis part today, but I couldn't, prepare the complex analysis conclusion on time. So I will touch back on complex analysis in the next class, but just kind of wrap things up by doing one of the integrals that we should have done, which would be instructive. But in the meantime, I want to go back to physics and talk about the more general solution to Schrodinger equation using Fourier analysis. Okay. So one thing we saw was that psi of x t and is a solution to the one-dimensional. It's a solution to the one-dimensional Schrodinger equation if it has this form, right? And for some, normalization constant, but we know that this is not a normalizable wave function. Okay? So you guys know about this. The other thing is that, I'm dealing with 1D, in 3D, this would become psi x vector xt, and here we would have e to the power plus I, the vector k dot vector x minus omega t. Okay, so whatever I say will have a very straightforward generalization to 3 dimensions. But for notational clarity, I will stick to 1 dimension. But it's really only for notational clarity. So now recall that k is related to p over h bar, right? And omega is related to the total energy over h bar. So we can write the solution, the wave solution, plane wave solution to Schrodinger equation as ce to the power. It's conventional, I think, to use a minus sign. Is it? Maybe not. Yeah. So this is so p x minus et. Okay. So this is the same solution. So if you were to write a 3-dimensional version of this, this would be ce to the power I over h bar, the 3 vector p, 3 vector x minus et. Okay? So now let's consider the solution at time t0. So then it is nothing but e to the power I, kx, let's not forget c, e to the power I, px over h bar, right? Now, if this is a solution, we can take an arbitrary linear combination. So let's call it psi, say, I don't know, psi p or something. Yeah. If this is a plane wave solution, then what is the time evolution of the solution? The time evolution of the solution is, well, it's just given by, we know this is I px minus et divided by h bar, right? But let's look at this guy. Then we can say that we can take an arbitrary linear combination. Let's just keep to 1 dimension. And we can say, okay, if I that say, let's call this SCP. Yeah, sorry. Yeah. So we can take an arbitrary linear combination, and the coefficients of the linear combination, let's call them AK over 2 pi. And, we can always absorb the 2 pi into AK. Then e to the power I kx dx, right? So now see that each of these guys, how will they evolve with time? If for time t greater than 0, each of these factors will become e to the power I kx minus omega t, right? And because each of these factor is a solution to Schrodinger equation, because Schrodinger equation is a linear differential equation, any arbitrary linear combination will also be a solution. And therefore, this expression, which is now a function of both x and t, it's a bona fide solution to the Schrodinger wave equation. And we can write it in a more physically revealing way by replacing k, by e, okay, let me just, I by h bar px minus et. So this should not be x, this should be k. And then we can say, okay, let's just go from k to p as our integration variable. And if I do that, then I will have, okay, there's a d k here. So if I do this, how is k related to p? Well, k is equal to p over h, right? So we will get 1 over 2 pi square root, and then there will be an h bar, and then a of k by square root of h bar. I think this is how we define, yeah, I think that's correct, yeah. D of p, and I think this is what we call AP, okay? There might be some factors of h bar that I'm getting wrong here, but that's not the most important thing. So by linearity, what we just said, that this is the general solution to the Schrodinger wave equation because each plane wave is a solution. Okay? So, so we get the time dependence of the Schrodinger wave equation. Okay, any questions?
Are these all the linear combination of e to the power I by I px minus et?
Exactly, yeah. So, what kind of linear combination it is will depend on this function, right? So for example, suppose that you are looking at a pulse, say you're looking at some given time. Suppose at given time, t is fixed, your wave function looks something like this, okay? So psi x of 0 or t0, this is what x looks like. Then, once you can, this is something I will do in the next class when I come back and introduce direct delta functions and stuff like that. You can work out what AP is, and AP is going to be, AP at that, AP is going to be, well, the thing is that for the Gaussian, the Fourier transform of the Gaussian is also a Gaussian, okay? So AP will be like that. The other thing is that this is, we are solving the time-dependent Schrodinger equation. We are not solving the time-independent Schrodinger equation. So here we are looking at, say, wave packets, right? So, the Fourier analysis is really useful when you are looking for solutions where the particle is a free particle. It's it can have some potential energy, but it's not necessarily bounded. The comment I wanted to make is so the energy and the momentum of a particle are not always going to be simultaneously measurable, okay? So the energy, we'll see that the energy, which I'm writing as H suggestively because it's a Hamiltonian, is going to be p squared by 2m plus v of x, okay? And we will see soon, and it depends on a lot of technical, like a lot of machineries that I still have to introduce, is that in quantum mechanics, this momentum is going to be an operator. And that's something that we'll discuss today. And the position is also an operator. And the consequence of them being operator is that you cannot measure them simultaneously. So as a result, when you have a non-trivial potential energy, the total energy and the total momentum is not something you can measure simultaneously, okay? So when we are looking at particles which are bound states, we are more interested in finding out what their energies are. And in that case, it is not necessarily true that that wave function will represent a well-defined momentum of that particle, okay? So for today, I'm just going to state this as a fact, and next time I will prove this. So if psi of x of t is given by 1 over square root of 2 pi h bar, a of p e to the power I h bar px minus e of t, and this is actually not very hard to prove. What is a of p? So a of p is given by the Fourier transform. And you can show that, by starting at time t equals to 0, this will be given by psi of x of t e to the power minus I by h bar px minus et d of x, okay? So this is the wave function. And we say it's a wave function in position space. And this is the wave function in the Fourier transform, and you will see this is the wave function in momentum space. Okay. And you'll notice that their definition is slightly asymmetric, because the momentum space wave function is not time dependent. Okay. And I will give you a proof of this in the next class. But in the meantime, I invite you to try to prove this yourself. Okay.
Sir, I didn't understand this part. Like psi x comma t is in a of p, and this a of p is in another equation that equates to psi of x xt.
Right. So when we were just doing Fourier analysis, if you had a function which was of this form, when we took, this was the Fourier transform of this function, right? If the function was a well-defined function with L squared norm, that this was given by ikx of dk, right? And then its Fourier transform, which is ak, is defined by, and by, in this way, right? Why was it?
So one is the coefficient in front of the function, and another is the function itself.
Exactly. So, but now these are like the Fourier transform of each other. But when we come to physics, there is time dependence, and the time dependence, of the wave function is given by this factor. Okay, by this factor, and because of that, the momentum wave function essentially has a time dependence in here and a time dependence here, in such a way that the momentum wave function is time independent. Okay, it's defined in that way. And so this is basically what I'm saying here is the generalization of this for time dependent case, and I will derive this expression in the next class. Okay, but I'm giving it to you here for completeness.
Okay, so one last question. That you said this is the linear combination, but this is we aren't seeing any infinite sum of a0, a1, a2, and
You are. The integration is a summation.
oh, okay, got it.
Right. So that we are going to the continuum limit, and the sum becomes an integral. Okay. When we went to the L going to infinity, delta k goes to 0 limit, the sum became an integral, right?
Okay, now understood.
Okay. Any more questions?
Sir, like, why are we doing this Fourier transform, the Fourier function? Like, what does it help us with?
Yeah, that's a very good question. So it's it helps us understand our system a little bit better. So, for example, suppose that we have a wave packet like this, okay? And its width, delta psi, is very small, right? So that means that if I do the Fourier transform of this, so this is what psi looks like at some time, it's the A will look like this. I'm just like being very heuristic, and this is going to be delta of A. And because of Fourier transform, we know that delta of psi will be inverse of delta of A with some h bar over here, okay? And there's something we will do. So what is delta A? Delta A is a function of P. So that means that delta, so yeah, here we can say delta A is h bar over delta psi. So if I know like what is the range of the wave function is going to be, I can say something about what would be the expectation value, what would be my expectation of the distribution of the momentum, right? Which would be given by AP. So that's a physical information that we can read off from doing Fourier transform.
So we're like seeing both situations for the momentum space and the position space.
Exactly, yeah. Fourier transform allows us to go to the momentum space, and then momentum space has more of, for the free particle, it has more of the energy information and also momentum information, right?
Yeah.
In the momentum space, are the axes p and x?
So it's px, py, pz, the three components of the physical momenta.
Okay.
Okay, so these relationships have a generalization in 3 dimensions. X psi of xt is going to have 2 pi h bar square root cubed 3 integrals a, which is a function of the 3 momentum p, e to the power I by h bar, p dot x minus e of t d cubed of p. And then a of p is going to be given by 1 over 2 pi h bar square root cubed, basically 3 Fourier transforms, right? Psi of x of t e to the power minus I by h bar p dot x minus et d cubed x. Okay, so these are the generalization of the Fourier transforms into 3-dimensional case.